Hello all. My name is Ami Munshi, and today we will discuss ant system algorithm using one problem of traveling salesman. So in this problem, the salesman has to traverse through all the cities, has to visit all the cities in the minimum, or he has to find the shortest route while he is going through all the cities, and he cannot visit any city twice. So important parameters in ant system algorithm are pheromone level on every edge, distance of each edge, probability that would be calculated dependent on pheromone levels and distance, and the evaporation rate. So pheromone level or pheromone is a chemical which is secreted by actual ants when it is traversing through any path. So that concept has been taken into account in this particular algorithm. Also, evaporation rate is rate at which the pheromone level will evaporate. So these are the few parameters which will be used in this algorithm. So I've taken or I've studied this algorithm from this particular paper. It's a very good paper, a must-read paper. So you can have a look at it. Uh, in this algorithm, we will be using some equations. So for example, one equation here is given for tau. Tau is the pheromone level. So this pheromone level would be updated after every iteration. And here this equation is the pheromone level equation without evaporation taken into consideration. We can also take pheromone level into consideration, and this will be the equation. In our example, we will be using this equation. We discuss this equation in detail when we actually go through the problem. Similarly, there will be one more equation that we will be using is of probability. Probability will be calculated dependent on based on the pheromone level and eta. Eta is reciprocal of the distance of that particular edge. So tau and eta will be used to calculate probability of any given edge, probability of taking that particular path. Alpha and beta are the control parameters, and alpha and beta will determine how much importance do we give to the parameter pheromone level and parameter of eta. But in our example, we have taken alpha and beta equal to 1, just for simplicity. So this is the example that we are going to do. The distance matrix is given. So there are 4 cities, A, B, C, D, and distances between all the cities is given here in this matrix. There is one more matrix which is given here, which is for initial pheromone level. So we assume that every path has got some fixed amount of pheromone level, which is equal. For our example, we have taken this level as equal to 1. Sorry, this thing should be equal to 0. So B to B, it should be equal to 0. Pheromone level should be equal to 0. So this distance matrix is now represented in form of graph just for better understanding. The same thing we have done for pheromone matrix as well, represented in terms of graph. So now when the ants, so yeah, in this problem, we have assumed that the starting point would be city A. And we have also assumed that there are 2 ants and both the ants will start at city A simultaneously. So when the ants are at city A, and if they want to start their journey, the next city which they can visit is city B or city C or city D. So we need to calculate the probability of going or taking path AB or path AC or path AD. And for calculating that probability, we will be using this equation here. So probability of taking path AB. Okay. For that, let us plug in the values of this tau and eta in this equation. So tau for path AB, here I is A and J is B. So tau for path AB is equal to 1 because that is our initial pheromone level that we have assumed. Eta of AB, eta of path AB. Eta, if you remember, it is reciprocal of the distance of that particular edge. So distance of edge AB is equal to 5. So eta for path AB will be equal to 5. Alpha and beta, we are assuming it to be equal to 1. So we will take it as 1. And so hence the numerator would be equal to 1 into 1 upon 5, which is eta. And the denominator would be summation of all tau and eta for all the 3 paths. So the first term here is due to the path AB. The second term here, 1 into 1 upon 6. 1 upon 6 is eta for path AC, and 1 upon 7 here is eta for path AD. So hence the probability that we get is 0.39. Similarly, we calculate the probability for path AC and AD. Only the numerator will change for those probabilities. Denominator would remain the same. Hence, probability of path AC would be 0.32. Similarly, probability of path AD would be 0.28. So all the three probabilities are listed here and we calculate the CDF. Now, for selection of which particular city would be visited after city A by ANT1, for this selection, we will use Roulé-Wheel selection algorithm. Now, what happens in Roulé-Wheel selection algorithm? Here, we generate a random number and we find out that that random number belongs in which range of CDFs. So for that particular range, when we identify the range in which the random number lies, for that range, we look for the upper limit of the number. And whichever city corresponds to that upper limit would be the next city to be visited. So that is mentioned here in this slide. So for example, if the random number generated for ANT1 is 0.45, then that 0.45 lies in the range of 0.39 and 0.71. And hence, the upper limit is 0.71. So the next city which would be considered to be visited would be city C. City C is selected as the next destination for ANT A. Now, from city A, ANT1 would be going to city C. Now, from city C, ANT1 can go to city D or city B. Hence, we again need to calculate the probability of taking path CB or taking path CD. These probabilities are calculated here, which is 0.6 and 0.4. Again, we find out the CDF and let us assume that now the random number which is generated for Roulé-Wheel selection is equal to 0.5. 0.5 lies in the range of 0 to 0.6. Hence the next city which will be visited would be city B. So now the ANT A has taken path A to C, C to B. After city B, the last city which has to be visited is city D. Here we need not calculate the probability because that is the last city which it has to visit. And hence the path now traveled by ANT1 would be A, C, B, D and back to A. The total distance covered by this path would be equal to 24 units. Now, if you remember, we have assumed in this problem that two ants have started the journey together from city A simultaneously. So, but both would have taken different paths. That is what we have assumed. So, for ant 2, we will repeat the same process. So, for ant 2 as well, from city A, we calculate all the three probabilities, which would be the same as ant 1. Then again, we use Roulé-Wheel selection algorithm. Let us assume that 0.83 was randomly generated and hence the next city which was selected was city D. After city D, the next city to be selected or visited was city C and hence the path taken by ANT2 was ADCBA with a total path length of 17 units. Now these two distances, the path length of the path traversed by ANT1 which is 24 units and length of the path traversed by ANT2 which is 17 units. These two distances will be used to update the pheromone levels of each edge. So let us look at that calculation. So now to update the pheromone level, this formula will be used wherein we have taken into account evaporation rate as well. We take the evaporation rate as 0.5. So now let us plug in values in this equation one by one. We will understand this equation one by one, each term one by one. So first of all, look at this summation here. Summation of k is equal to 1 to m delta tau ij of kth ant. So here m is equal to number of ants. In our example, we have taken m is equal to 2. So we just have 2 ants. And delta tau ij is the pheromone level contributed by each ant on that particular edge. on edge ij. So let us assume that we are thinking about calculating the pheromone level of edge AD. Okay, first of all, you look at this graph here. In this graph, we have shown the paths taken by ant 1 and 2. So blue line represents the path taken by ant 1, which is A, C, B, D, A. And green line represents path taken by ant 2, which is A, D, C, B, and A. Right? So let us calculate pheromone level for edge AD. Now, if you look at edge AD, ant 1 as well as ant 2 both have taken this path. So both the ants would have contributed to increase in pheromone level on this particular path. So that is represented by this summation. So if I take ij as AD, edge AD, ant number 1, if my k is equal to 1, ant number 1 will contribute 1 by Lk, that is 1 by distance covered by ant number 1, that is 1 by 24. That would be contribution by ant 1, and ant number 2 will contribute 1 by 17. So in total, ant 1 and ant 2 will contribute 1 by 24 plus 1 by 17, which we will put here in this part of the equation. Now, here, tau ij, this tau ij is tau AD for the updated tau AD that we will be calculating. Rho would be equal to 0.5, which we have put here. And this tau ij is the previous level of the pheromone. So we have assumed the initial level of pheromone as 1. So here 1, we will plug in the value 1 in this tau ij. So this is how we get value of updated tau AD, which is equal to 0.6. So 50% of previous pheromone level is considered, plus this is the new contribution by ant 1 and ant 2. So tau AD is equal to 0.6. Similarly, we calculate the pheromone levels for all the edges. So for example, if we look at edges AB and DC, we can see that only ant 2 has traversed through this path. Ant 1 has not traversed through this path, and hence the contribution will be only by ant 2 towards the pheromone level, which is equal to 1 by 17. Your 1 by 24 term will not be there. Similarly, for path AC and path BD, only ant 1 has traversed through that path, and hence the contribution by ant 1 would be 1 by 24. There will be no contribution by ant 2. So that is how we calculate the updated pheromone levels of each edge. This will be put in a matrix here. Now this matrix could be used for further calculations. So if we want to find out if some other ant comes at city A, and if that ant has to now take the journey, then this pheromone matrix would be used to calculate the probability of each path. So this is where we end our video. Thank you very much for listening.